Okay, so before we begin, are there any questions? All right, so where we left off, or where I want to start anyhow, is I want to look at exercise 12 on page 222, which is called the MG1 queue with server vacation times. So this is exercise 12, page 222. And this is the MG1 Vacation Model. And although it doesn't use these words in the statement of the problem, this is for the particular case of what's called exhaustive service. I'll get to that shortly. Now your homework, your next homework assignment is based on this, and also you have the details of this worked out in the solutions manual. So I just want to review pieces of it. So the idea is this. You start off with a queue that otherwise would be MG1. So let's say that, that this is the station, and the customers arrive. And here is the server. And the server works until it's idle. That is, while it's working, other customers can be arriving, but eventually the server becomes idle. So this is, in that sense, just like ordinary MG1. However, when the server becomes idle, then the server takes what's called a vacation. So we can view it like that. And since the server takes a vacation, let me start to say it this way. When the server returns from vacation, if there is nobody there, then he takes another vacation. So he keeps on taking vacations until for the first time he returns and he finds that there's at least one customer waiting. And then he serves that customer or those customers and all of their descendants, and he doesn't take a vacation again until there is no more work remaining at that station. Now, the idea, the fact that when he returns from vacation, he doesn't leave again until all the work at that station is finished. That's the exhaustive service part. So you could have cases in which the server takes a vacation at other times. But in the model I want to look at, which is the most basic model, the server works until there's no more work to be done, and then he takes his vacation. Now, he could be doing all kinds of other things during that vacation time, but the reason that this model was originally formulated was to take into account or help you analyze the case in which there are other queues or other stations, and you're serving these guys in cyclic order. So in other words, you're polling. This is a polling model. It's called a polling model because what that means is that as the server moves from station to station, it polls the station to ask whether or not there's any work waiting to be done. And if there is, then it serves it. And if there isn't, then it moves on to the next station. And if you take that point of view, then from the viewpoint of a particular station, the instant from which the server leaves that station until he returns again is a vacation. So the objective here then, the strategy, is to analyze the performance of this queue in terms of the vacation, and then to figure out what the vacation is. Now, when you analyze this in the polling model, the way you specify the length of the vacation is you write equations that determine the generating function of the number of customers waiting here after you return from a cycle, from a vacation. So in the analysis or definition of the vacation model, what we'll do is we'll assume that the length of the vacation is determined by this generating function, and then later we'll hook the generating function specifically to the polling model. So actually there are two pieces here. One is the vacation model, which is of interest for itself, and then the other is the use of the vacation model as a tool to enable you to handle the polling model. So that's the big picture here. So the way the vacation is defined is as follows. We define a generating function called f of z in which the P's, Pj, is the probability that when the server returns from a vacation, the number of customers it finds waiting for it is exactly j. So I'm not specifying what this P is. I'm simply going to solve the problem in terms of its generating function. Okay, so let me begin by writing the basic equation. So first of all, let me remind you about ordinary MG1. I just want to go through the main facts here. So for ordinary MG1, what we did is we embedded a Markov chain at the service completion epochs, like that, and we wrote equations like this. The probability, let's see, maybe I should give myself a little bit more room here. I think this will be all right. We said the probability that a departing customer, that's a star, leaves behind j others in equilibrium is equal to two pieces. One, we said, is, well, first of all, let's take the case in which j is 0. That is, the probability that he leaves behind j is the probability that the previous customer left behind 0. And in that case, then this guy will leave behind j if, what must happen? If the previous customer left the system empty, okay, if he leaves the system empty, then the next arriving customer will find the system empty. And so the number that he will leave behind, since he will be the next departure, will be the number that arrived during his service time. And we call that probability little pj. So little pj was the probability, this guy right here. That's the probability that during a service time, the number of arrivals, according to a Poisson process, is exactly j. Okay, now suppose that the previous departure did not leave the system empty. So suppose he left it in some state I, where I is greater than 0. Okay, what that means, that is, he did not leave the system empty. Okay, what that means is that he will leave behind j if this guy left behind I, and during the service that then begins when this guy leaves, exactly j minus I plus 1 new customers arrive. J minus I plus 1. And then we sum that as I runs from 1 to j plus 1. Because for I greater than j plus 1, then this probability is 0. Okay, so that's what we did for ordinary MG1. Now, the reason I want to write that down is now I want to write down the corresponding equation for the vacation model. All right, so now I'm going to, again, embed a chain at the service completion epochs, just as before. Now I'm going to call the probabilities pi j star caret or hat or something like that. Okay, so the hat indicates I'm talking about the vacation model, and the non-hat means it's the ordinary MG1Q. Now, in the vacation model, there are two possibilities here. Either when a customer departs, either he departs, well, either the previous customer left behind the system, left the server working, or the previous customer left the system empty, just as before. So I'm going to make the same distinction. I'm going to say that the probability that the departing customer in the vacation model leaves behind j is going to depend on what the previous customer left behind. And there are two cases. The previous customer could leave behind 0, so that would be pi star 0 hat. Or The previous customer could leave behind I where I is greater than 0. I'll call that pi I star hat. Okay, now let's look at this case, the case where I is at least 1. If the previous customer, when he departed, left behind at least one customer, then the server does not go on vacation. If the server doesn't go on vacation, then the number that he leaves behind, that the next customer will leave behind, will depend only on the number that this guy left behind, which was I, plus the number that arrived during his service time. So in fact, this term is exactly the same as this term. So this is going to be the sum as I runs from 1 to j plus 1 of pi I star, just give myself more room here, sum I runs from 1 to j plus 1 of pi I star p j minus I plus 1. So it's going to be exactly the same term as before. The only difference is the case in which the previous guy left the system empty. In the ordinary MG1 queue, if the previous guy left the system empty, then we know that when the server starts working again, there is always exactly one customer present. But now when the previous guy leaves the system empty, the server goes on vacation, and we don't know how many customers are going to be waiting when the server returns from vacation. But we know the generating function of that by assumption. Okay, so now let's write down the term that multiplies this. First of all, suppose that when the customer returns from vacation, the probability that he finds exactly k customers is given by pk. Well, if he finds 0 customers when he returns from vacation, then he takes another vacation. He doesn't stick around. So what we want is we want to know the number of customers that are waiting at the station when the server returns, given that there must be at least 1, because if there's 0, then he goes on vacation again. So first, I will multiply this. I need more room here, so let me move this out. Here's my pi. I think I need another. It seems that these black ones run out of ink faster than the blue ones. All right, so here is my pi hat star j. Now, pi hat star 0 is the probability that the last customer left the system empty, left the server idle, and so the server goes on vacation, exhaustive service. Okay, now when he returns, pk is the probability that there are k customers waiting at the end of the vacation. So pk over 1 minus p0 is the conditional probability that there are k customers waiting, given that there's at least 1. Because if there isn't at least 1, then the server takes a vacation again, doesn't stop. So when the server returns from vacation, if he stops, then pk over 1 minus p0 is the probability that exactly k customers are waiting. Okay, now, if k customers are waiting, then the server serves one of those customers, and then that customer leaves. How many does he leave behind him? Well, he leaves k minus 1 behind him, and so the situation is exactly the same as it was over here, in that this guy will leave behind j if during the service time of the first customer that the server serves when he returns from vacation, exactly j minus k plus 1 guys arrive. So I have here p j minus k plus 1. So this term is exactly analogous to that term, except that here I'm calling it k, and here I'm calling it I, to differentiate between the cases. And then I sum this just as before, as k, rather than I, runs from 1 to j plus 1. Okay, so let me go back over that. Because once you see the structure here, that makes everything simple. Okay, so first I look at ordinary MG1, and I recognize that there are two cases. Either the previous customer left the system empty, or he didn't. Now, the same is true in the vacation model. Either the previous customer left the system empty, or he didn't. Now, in both the regular ordinary model and the vacation model, if you know that the previous customer did not leave the system empty, then you know that the server is working, and therefore the number left behind by the next departure depends only on the number of customers that this guy left behind, that's the I, and the number that arrived during his service time, which in order for this guy to leave behind J must be J minus I plus 1. So this term and this term are exactly the same. The place where the vacation model differs from the ordinary model is when the previous customer leaves the system empty. If he does in the ordinary model, then the server just waits around, and as soon as somebody arrives, he starts to work, and therefore, when the next customer leaves, he'll leave behind J if during that previous service time exactly J arrived. In the vacation model, if the previous customer leaves the system empty, the server takes a vacation. The server will continue on vacation, and it'll take vacation after vacation until, when it returns, it finds at least one customer here. By assumption, PJ describes the probability that at the end of a vacation there are exactly J customers waiting at the station. So what we want is the conditional probability that the number waiting is K, given that it's at least 1. Because if it isn't at least 1, the server doesn't begin to serve but takes another vacation. Okay, now, if when the server begins to work, he finds exactly K, then when the server finishes serving the first of those customers, and we have the first service completion epoch, the probability that he will leave behind exactly J is the probability that during that service time, exactly J minus K plus 1 occur. So this term, except for the 1 minus P0, this term looks just like this term. If I took that 1 minus P0 outside, then this term is exactly the same as this term, except that what I've named K here, I've named I here. And of course, the probabilities are, in this case, are the probabilities associated with the vacation model that you're trying to find. And over here, the probabilities are the assumed given probabilities that describe the generating function that describe the length of the vacation. Question?
For the ordinary MG1, the K0 means that the previous customer leave 0.
That's right.
If we want the customer to leave with J, as the K0 start times should be time J plus 1, P plus 1, J plus
Here?
1. Yes, you have to have J plus 1 arrive. Then
No.
leave.
No, that's true over here. Look over here. Suppose that this customer leaves the system empty. Now we want to talk about the next departure. The next departure is right here.
Yes.
So if he leaves the system empty, then the next arrival will find the system empty. Now, he will then immediately enter service, and when he leaves, he will leave behind him all those that arrived during his service time. So he will leave behind J if during his service time exactly J arrived. The reasoning that
you don't count the 1.
I don't count. That's right. I count that 1 if there is no dead time in between. So your reasoning for this term, which is correct. Okay, there you have that extra 1. But if the previous customer left the system empty, then you know that the next customer will find the system empty, and when he leaves, he will leave behind him whoever arrived during his service time. You see, in this case, when a customer leaves the system non-empty, then you know that one of those guys is leaving. So there's a difference in the viewpoint. That's why you separated in ordinary MG1 the zeroth case from the non-zero case. Okay, now in the vacation model, I do exactly the same thing, and I recognize that the non-zero case is exactly the same. It's only the zero case that makes any difference. In the zero case, in the ordinary model, when the server returns, the number of customers that, shouldn't say returns, in the ordinary model, if the departure leaves behind 0, then we know that the server is going to begin to work immediately with the next arrival. But in the vacation model, if the last customer leaves behind 0, we don't know how many customers are going to be waiting when the server starts to work. But we know that the probability that there will be exactly J at the station at the end of the vacation is given by these probabilities with this generating function. So we take this probability, except now I'm going to call it K. I'm making the index K here. Except that I divide by 1 minus P0 because I want the conditional probability that when the server begins to work after return from vacation, it finds K, given that K is at least 1. Because if K is 0, then the server doesn't begin to work but takes another vacation. Okay, so eventually, with probability Pk over 1 minus P0, the server returns from vacation and finds some positive number K of customers waiting. And from that point on, it doesn't matter whether how those customers got there. All that matters is that he starts to work, and when the first customer leaves after the server returns from vacation, the probability that he will leave behind him J is the probability that during the service time of that customer, J minus K plus 1 arrived. Now it's exactly the same as this. So this term and this term are analogous. And of course, that makes the arithmetic easier, because you remember that in the MG1, what we did is we called that S, and then we did some manipulations. We had a double sum, and this all reduced to something. Well, now, this is exactly the same thing. You don't have to do the work anymore, because you get exactly the same result here, except that you factor out the 1 minus P0, and you change the name of the generating function of this from the original G to the generating function of this, which is the F. And that's how the generating function of F gets into the answer. Okay, so in other words, what you did before was you defined G of Z to be the summation of pi J star Z to the J. And now you define G caret, or G hat of Z, to be the sum of pi J hat star Z to the J. So you do the same thing you did before. You multiply through by Z to the J and you sum, except that now the generating function you're looking for is the one with a hat. And so this term will be the same as this term. This term will be different from this, but it'll be the same as this, except that it'll have this constant, which you can factor out, irrelevant. And what you have over here is, instead of the generating function of the pi star hats, you have here the generating function of the pKs, which is in fact F. Okay, so what the problem asks you to do is to do that work, which is actually easy once the equations are written. The common mistake is to forget the 1 minus P0, to forget the condition. That's one mistake. And the other is just not to recognize that there's no new algebra here, because the algebra associated with this term is the same as what you already did. So that actually makes things very easy. So it looks complicated, but it's not. Okay, now when you get done, what you do is you get an algebraic equation just as before. Before you got it for G, now you're going to get it for G hat. Except that this G hat is now going to contain in it the F, which came from this term. So the homework problem asks you to prove that if you write those equations, then you will get equation 2, which is f of z minus 1 divided by f prime of 1 z minus 1 g of z. Okay, now this is amazing, sort of. First of all, the f prime of 1 comes about because, as before, you had to get the pi 0 term. And you have to use L'Hopital's rule, and so that's where the derivative comes from. Okay, now the f prime of 1, of course, is the average or expected number of customers that are waiting in the target station when the server returns from vacation. Now notice that this G is the product of two pieces. One of them is this term here, which doesn't depend at all on the service time distribution or anything except F. So this has to do only with the vacation, because the only thing that's in here other than the dummy variable Z is F. And all of this stuff associated with the service times and the arrival rate is right in here, because this is the same G as before. So in other words, the generating function of the number of customers left behind by an arbitrary departure in the vacation model is the product of two pieces. It separates out. One of those pieces is just what you would get in the ordinary MG1 queue, where there are no vacations. And the other piece has to do with only the vacations. Now, it turns out that this is also a generating function. And in fact, this is what I'm asking you to show in the homework, although it's easy once it's pointed out that it's true. This thing right here is the same thing as what I'll call f tilde of z, which is the PGF of the number of Poisson arrivals during a vacation. During a forward recurrence time. That's important. Forward recurrence time of a vacation. Okay, so first of all, let's assume that that's true. If this turns out to be a probability generating function, then what that means is that this probability generating function is the product of two probability generating functions. And therefore, the random variable that it represents has the same distribution as the sum of two independent random variables, one of which has this generating function, and the other of which has this generating function. So what this says, amazingly, is that when the server goes on vacation, let's imagine that there's a renewal process in which the intervals in the renewal process are vacation intervals. Vacation 1, vacation 2, and so forth. And let's suppose that the vacations are IID. Now, no one in the formulation of the model, that wasn't required. But if there were such a process, like that, then if I interrupted that process at random, there would be a forward recurrence time. And if I had Poisson arrivals occurring during this interval, then this term right over here is the generating function of the number of customers that arrive according to a Poisson process during a forward recurrence time of an interval interrupted in a renewal process in which the renewal intervals are the vacations. Okay, so that's amazing. You know, it's amazing in several different aspects. Now, this is the fact that this thing breaks up into a product, and each of these is a generating function. is what's called decomposition. Of course, the word decomposition is used all over the place, but that's its meaning in this context. Because what it says is that the random variable that this generates can be decomposed into a sum of two independent random variables, one of which has the distribution that you find in an ordinary MG1 queue without vacations, and the other of which is something else. And that something else is exactly the number of customers that arrive according to a Poisson process during a forward recurrence time of a renewal process that is composed of vacations. Now this is amazing, first of all, because it decomposes. Second of all, because this first term has this particular interpretation. So what this says is that if you take the viewpoint now, if we use the fact that in the vacation model, since arrivals and departures occur one at a time, we can apply the theorem that says that the probabilities from the viewpoints of the arrivals are the same as the probabilities from the viewpoints of the departures. And therefore, what this says is that when a customer arrives in the vacation model, the number that he finds in front of him can be viewed as a sum of two pieces. One is the number that he would find if there were no vacations, and the other is the number that arrived during a partial vacation, an interrupted vacation. Now, this is not true in a sample path sense. By that I mean that if you look at a particular customer, you cannot break his waiting time down. You cannot say that his viewpoint is, for each particular customer, that what he sees is this number plus that number. Because when a particular customer arrives, either he arrives during a vacation or he doesn't. And if he doesn't, then he doesn't see what ordinary MG1 sees, because he sees a queue in which the server has been removed from work for a time. On the other hand, if he arrives in the middle of a vacation, then he doesn't necessarily see just those customers that arrived during a forward recurrence time. In fact, he sees those customers plus the other customers. So for an individual customer, he does not see this part and this part. But statistically speaking, whatever it is he sees factors into those two terms. Now, from the viewpoint of the polling model, this greatly simplifies things, because it says that whatever the interaction is between these queues, all I have to do is find that in terms of this generating function. Because whatever waiting time is going to be experienced by a customer arriving to this target queue is going to be just what he would have if these other queues didn't exist, plus something that has to do only with how long it takes the server to go through the other queues and nothing to do with the queue itself. Now, how long it takes to serve the other queues is affected by the queue itself. But the point is that the service time distribution of this MG1 queue does not appear explicitly in here in terms of this formula. Of course, when I have to evaluate this thing, then it may be in there because I've got to write equations that are going to determine those things. Of course, that's in a polling model. If it's not a polling model, then who knows what this might be. It could be anything. And in fact, that's part of what the homework problem asks you to evaluate. For example, one of the things it says is, suppose that we look at the ordinary MG1 as a special case of this. For example, I could say that I'm going to pick this F to describe the case in which the vacation always ends at the instant that the first customer arrives when the servers become idle. So that even though as the server is someplace else doing whatever work it does, as soon as a customer arrives here, the server immediately jumps back. So that's a vacation model, but obviously it's got to give you the same answer as an ordinary MG1 queue, because in effect, in an ordinary MG1 queue, the server can be on vacation as long as there's nobody's there. but he has to be ready to begin work as soon as somebody arrives. So one of the questions in the homework problem is to show that if and only if the server always begins service at the instant that the first customer arrives to the target station, to the queue, then the vacation model and the ordinary MG1 model coincide. So the vacation model then is a generalization, a very powerful generalization of ordinary MG1. Now, in part D, it asks you to show that something is true. Okay, so let me erase this. Notice again, I kept on emphasizing in renewal theory over and over again that this renewal theory result shows up all the time. There's no reason why that should be true that I could see. It just comes out of the mathematics. Once this is done, which is arithmetic, once this is done, then this is simply easily recognized as exactly what you would get if you calculated the number of arrivals that occurred during a forward recurrence time of a vacation if the arrivals occur according to a Poisson process. Then that's what you get. So once again, this same renewal theory result appears, and that means that the same effects that you had that you found in your last homework, like for example, the case where making the inter-event time in the renewal process longer actually makes the waiting time until the end of until the next renewal smaller. The same effect could be in here in the vacation model. That is, making the vacation longer actually makes the waiting times less because it has the same piece in it. This renewal theory comes up all the time. All right, now suppose you take this and you find G tilde prime. You differentiate both sides of this and evaluate it at 1. Well, if I differentiate that, this is a product of two things. So that means that I'm going to get the derivative of this times this plus the derivative of this times this. Now, when I have the derivative of this times this and I set z equal to 1, then this g of 1 is simply 1. So that's not going to appear. It's just going to be a 1. In the case in which I have the derivative of that, then this part, since it's a generating function, is going to be 1. And the derivative of that one evaluated when z is equal to 1 is the mean number in the ordinary MG1. So if you do that work, just take that derivative, then what you get is this. You're going to get g prime of 1 plus f double prime of 1 divided by 2 f prime of 1. So what this says, by differentiating this, is that the mean number in the vacation model is equal to the mean number in the ordinary queue without vacations plus a piece. And that piece, of course, from this argument here, is exactly the average number of arrivals according to a Poisson process during the forward recurrence time of a vacation. So by L equals lambda W, then, the waiting time in this model is going to be the sum of the waiting time in this model plus the sum of that forward vacation time. In other words, it turns out, this is one of the questions that you're asked to do, if you calculate the Laplace-Dirichlet transform, assuming FIFO service, going from here to here, just the same way we went from here to the ordinary omega, the same argument, then what you will get is omega of s times v tilde of s. This is equation 4, although in 4 it isn't written that way. Should be. So this says that the waiting time in the vacation model is its transform for waiting times with FIFO, and it's derived by exactly the same argument by which you derived this for ordinary MG1. Okay, the same argument that Kendall used. And you say, okay, if I just do that now, then I see that I get the analog of this thing right here, which is that the transform of the waiting time in the vacation model is the transform in the ordinary MG1Q without vacations times another transform, and that transform is the forward recurrence time of the vacation, of an interrupted of a vacation in a renewal process, which means that the waiting time has the same distribution as the sum of two independent random variables, one of which is the waiting time in the ordinary MG1 without the vacation, and the other is the forward recurrence time of a vacation. Now, if I differentiate this to get the expected value, let's see, I guess I have room, I'll do it right here. If I differentiate that, that is, I take the derivative with respect to s, set s equal to 0 multiplied by -1, then I will get that the expected value of the waiting time in the vacation model, okay, that's minus omega hat prime evaluated at 0. So I differentiate through this, and what I get is, when I differentiate that piece, just like over here, I'm going to get the expected waiting time in ordinary MG1, and then I'm going to get this piece over here, which is exactly f double prime of 1 divided by 2 lambda f prime of 1. And of course, I can get this by differentiating, but I don't have to. I could get this by L equals lambda W. Because if I divide through by lambda, then that thing becomes that. And this thing becomes this. There's the lambda. Except that, remember that this, when I divide through by lambda, this gives me response times. I have to subtract off on each side the average service time to go from response times to waiting times. Okay, so this thing is also called decomposition. Well, these are all decomposition. This is decomposition in number. This is decomposition of average in number. This is decomposition in time, in waiting time. And this is decomposition in average waiting times. So now this vacation idea is very powerful because it means that lots of different versions of MG1 where the server is away doing some other priority work can be analyzed by analyzing the vacation separately, in a sense, from the rest of the problem. That is, you can break it down into two pieces and then put the pieces back together. All right, so your homework asks you to work all this out, although, as I say, once you write these equations, it's easy. So you go through the algebra, and then everything leads you along. And the only thing that's not in the solutions manual, which is really important but represents my ignorance at the time, is this piece right here being identified as that, and correspondingly, this piece right here, well, when I work this out, the second piece, this piece being identified analogously as a product of that and that. Okay, so the homework, so what's in the solutions manual in the textbook simply doesn't identify this second piece, doesn't interpret what it is. But of course, it's only one step because all you have to do is recognize it, except that actually it was recognized at that time. Let me give a little bit of history of this. This problem was first analyzed by myself and Grace Murray in 1969. Cooper and Murray. We were at Bell Labs at the time, and this was the first paper for both of us. And we analyzed this, but we couldn't get waiting times. All we could get was, although it was very complicated, was we got expressions for the generating function of the number of customers in each queue when I switched from one queue to the next. And then the second paper, which was by myself in 1970, was the one that recognized that if you can define this as a vacation, although vacations hadn't been defined at that time, that was the point, but that if you took that viewpoint that maybe something would work out. And so in that paper, in the 1970 paper, first the ordinary exhaustive service vacation model is defined, and then it's applied to this model for the purpose of finding an expression for the mean waiting time in any one of these queues. And that was in 1970. In 1975, Levy and Yekiali wrote a paper looking only at the vacation part, and they identified this term as that term. But still, there wasn't much action along this front for several years. And then what happened was I guess there was a confluence of things that turned out to be very fortunate. One was that I left Bell Labs in '69, and later somebody named Furman, write these names down here, S.W. Furman, F-U-H-R-M-A-N-N. Furman was working at Bell Labs in the same department that I had worked in, and his assignment was to go back over the stuff that had been done earlier and continue that work. And what he did is, when he started working, he contacted me and we discussed some things, and he came up with an easier proof for this stuff right here, for the case of exhaustive service. And then he realized that actually you could get decomposition theorems for the case in which the service was not necessarily exhaustive. And so in 1985, we collaborated and wrote a paper together it's called something like MG1Q with generalized vacations or something like that, by Furman and Cooper. And in that paper, we gave conditions for decompositions of this type and this type that were more general, had generalized vacations, that is, didn't require necessarily exhaustive service, but could have other kinds of service, such as gated service. Gated service, what happens is this. Let's say that here's the station, and let's say that the server goes on vacation. When it returns from vacation, whatever customers are waiting there, if there's at least one. If there's none, it goes on and takes another vacation. But if there's at least one customer waiting there, then it closes a gate. And it serves only the customers in front of the gate. And then any customers that arrive after the gate are served on the next cycle. And so on. And so that's called gated service. And it turns out that in that case, and in other cases as well, that you get some kinds of decomposition. So a combination of things happened. Furman came up with this nice idea, and luckily for me, I got to be the second author on this paper. And this turns out now to be a well-known paper. This is cited quite often because this paper generalizes this decomposition idea and identifies, makes all these identifications, really tells the whole story. And in addition, it makes these polling models much easier. And polling models all of a sudden started to get popular because they describe what happens, for example, in local area networks. In a local area network, you've got a bunch of queues. That's a polling model. And when the server finishes serving a station, then it passes a token. That is, it releases a signal, and the signal is grabbed by the next station in the logical sequence that has any work to be done. And so and at that time, that station then captures the transmission channel. And then when it's finished, it releases the token, and the next station has access to the transmission channel and so forth. So for local area networks, then, this gave a way of computing the average waiting time. So of course, then this became a very practical problem. In addition, people started worrying more about manufacturing systems, and they also seem to fit somewhat into this framework. So now it turns out that there's a whole literature on this kind of stuff. Takagi in Japan wrote his dissertation under Kleinrock on polling systems, and that was in the mid-'80s. And since then, he has sort of maintained a library, in a sense. He's sort of like the world's clearinghouse for information about polling models. And he's also very prolific, so he's written many papers and several big, thick books about polling models and vacation models. So partly because of his efforts at collecting everything in one place, partly because of this confluence of results. One being the mathematical result with vacation models that allows you to separate things, and that allows you to solve polling models, and polling models have important applications. So we have, from the viewpoint of vacation models, you've got questions of mathematical interest, because there are other kinds of vacation models now. This can go on endlessly. And the question is, in general, when does decomposition occur and when doesn't it occur, and why, and what does it mean, and so forth. And the second is that in polling models and other more complicated models where you have priorities, then these results can actually be used. And so the combination of the mathematical interest plus the utility makes this an area that's attracted a lot of attention. And probably since 1985, I guess that's when sort of the dam broke. So even though it started in the late 60s and 70s, it wasn't until around here that the number of papers went from maybe 5 to now probably thousands. There's probably literally 1,000 papers that have been written on polling models and vacation models. And it's gotten to the point where the papers on vacation models and polling models are so complicated that I can't understand what's going on. I mean, it's my model, but I don't know what they're doing. They're writing in Banach spaces, and I don't know, all kinds of things that I can't figure out. But it's always, it's nice to see that. Okay, so one of the things I'm going to do in the course is I'm going to do some more on vacation and polling models, and that's why I'm giving these homeworks. And the hope is that some of you will be wanting to do things like a master's thesis or a PhD dissertation. In terms of master's thesis, there are some interesting questions that we're just beginning to understand mathematically, and these things can all be tested through simulation. And so it's nice, reasonable master's thesis, I think, for somebody to write a simulation and optimize it, design it to answer specific questions that for which we have only conjectures, or maybe to verify calculations, or to just explore things and see what happens. And it's not, if you know what you're doing, I don't think it's all that difficult, because anybody in a sense can write a simulation. It's just a matter then of being systematic and searching through it. Okay, so that's all I want to say at the moment about the vacation model, but you might have some questions when you start to work on it. Okay, any questions at the moment? But I'm going to do some more of these exercises, I think. Like, I think I might get back to exercise number 14, the MG1Q from the viewpoint of arrivals. But before I do that, I think I'm going to go to page 228 and start talking about the busy period. And then I may or may not get back to some of these other exercises. Okay, so I'm on page 228, the busy period. The busy period is something that turns out to be very important in the analysis of polling models. Okay, so any questions before I erase this? This stuff is really interesting, and I'm still working on these vacation and polling models, and there are still surprising things to be done, even though literally now hundreds or maybe 1,000 papers have been written, and it's been altogether 25 years, say, since the beginning of this subject. If anybody's interested, let me know, and I'll give you the names of the references for example, Takagi's dissertation, his books. And Takagi, every several years, writes a survey paper in which he updates polling models. So that makes it easy to do research because he keeps everything in a nice standard format. So you can, when you consider all of the different things that can be varied, all the different models there are, it's nice to have all this stuff written down in one place. Okay, so the busy period. B-U-S-Y, period. We've already seen something about the busy period when we discussed the MG1 LIFO preemptive resume. Consider a single server queue. Let's say that I'm going to draw a graph here in which this represents remaining work, or what's sometimes called virtual work. Now, let me call it remaining work. It's called virtual delay. Get to that in a moment. So here's the remaining work. So a customer arrives, and when he arrives, he brings with him an amount of work equal to his service time. So the graph jumps up by that amount. And then the server works off that work at unit rate, 1 unit of work per unit of time. So the amount of remaining work decreases with slope -1 until either it crosses 0 and the server becomes idle again, or a new customer arrives. And then the graph jumps up by that guy's service time, and so on. So you get a picture that looks like this, sort of this sawtooth curve here. And the busy period, by definition, is the length of time from when the server starts to work until it's idle again. So that's the busy period. And one of the things you'd like to know is how long is a busy period, and how many customers are served during a busy period, and things like that. Now this, it turns out, is of interest, not just because it might be a measure of performance in itself, or is of interest in itself, but it turns out to be a piece of the bigger picture. Just like over here, the vacation decomposition breaks things up into, and allows you to look at bigger pictures. Okay, so in order to analyze the busy period, first of all, let's start with something that's a little bit bigger than that, a little bit more general, called the J busy period. Oh, and let me go back before I get into the J busy period. I mentioned something about what's called virtual waiting time. Virtual means not real, or not literal. Now, suppose this is an MG1 queue with FIFO. Remember, I haven't said what the order of service here is, because that doesn't matter. That doesn't affect the amount of work. It only affects the identities of the individual customers. But suppose that I have first come, first served service, or FIFO, first in, first out. Then, if a customer arrives at random, at any point in time, if you were to look at this, then the height of this graph is the amount of waiting time that there would be if that were an arrival instant. So if I can figure out for remaining work, if I could figure out the height of this graph as a function of time, then by pasta, I can calculate the waiting times. Because in the graph, when the graph is drawn, of course, the arrivals cause the jumps up. But by pasta, what the arriving customer sees and what the outside observer sees are statistically the same as long as you have Poisson arrivals. So that means that the height of this graph at any time is the amount of time that a customer would wait if that instant were an arrival epoch. And by pasta, then that in fact gives the distribution of the waiting times from the viewpoint of the arriving customer. So for that reason, the graph is sometimes called the graph of virtual waiting time. Okay, now, the J busy period. The J busy period, by definition, is a busy period that begins with not one customer present, but J customers present. So a J busy period might look like this. let's say that a customer arrives and the server doesn't do anything, and that's the service time of that customer. So no work is being done. And then another customer arrives, and the work jumps up, the remaining work jumps up by his service time, and so on. And let's say, for the sake of argument, that at this instant right here, the server now begins to work, and now you get the same kind of diagram you had before. So if I measure the busy period from the instant the server starts to work with J customers present, then that length of time is called the J busy period. So therefore, a J busy period with J equals 1 is the same as an ordinary busy period. Now, the reason I want to look at this is I want to look at the distribution function of a J busy period. You'll see one reason why in a moment. So by definition, this is the distribution function of a J busy period. It's the probability that a busy period that begins with J customers present lasts less than or equal to T. Okay, now according to equation 861, we have the following. As I've already argued, the length of the busy period depends only on the amount of work and not on the order in which you serve the customers. So if I want to find the length of a J busy period, the kind of intuitively obvious way to do it is to simply imagine that there's J customers and ask how long it takes until they and all their descendants are served. But I don't have to look at the customers as being served in that order. Suppose that I have a J busy period. So at the start of the J busy period, there are 3 customers, say, J customers, this diagram 3, that are waiting. So instead of serving those customers in their order of arrival, what I'll do is I'll take the first customer and I'll serve him and all the customers that arrive during his service time, and then all the customers that arrive during their service times, and so forth. So in other words, the way I serve the J busy period is I first serve a 1 busy period. Okay? Let me say that again. All right, we've got, say, 3 customers when the server starts to work. One way I could serve this J busy period is I could serve this customer, this customer, this customer. Then I could serve all of the customers that arrived during their 3 service times. Then I could serve all the customers that arrived during their service times, and so on. And when I got all finished, that would be my J busy period. But the other way I could do it is I could serve this customer, and when I get finished with him, I don't serve these guys, but I serve the customers that arrived during his service time, if any. And then I serve the customers that arrive during those service times, if any, and so forth. And I don't start on this customer until this customer and all his descendants are served. So how long does that take? Well, until this guy and all his descendants are served, that's a 1 busy period. That's a busy period that began with 1 customer present. Okay, when that's finished, I go to this customer, and I serve him and all his descendants. But the length of time I spend serving him and his descendants is independent of the length of time I spend serving him and his. And the same for this. So therefore, the length of time it takes me to serve all the customers in a J busy period is the sum of J independent identical random variables, each of which has a distribution function of a 1 busy period. Okay, so if I define B of t as the distribution function of a busy period, and notice that, of course, that's the same as a J busy period with J equals 1, then this thing is the same as the J-fold self-convolution of the distribution function of a 1 busy period. So this result, which is strictly combinatorial, intuitive, no calculation, will turn out to be very important, very useful. You can see there's a lot of little tricky factors in here. Okay, now, the reason I want to do this is that if I define beta sub j of s to be the Laplace-Dietrich transform of the distribution function of the j busy period, then that, of course, is the distribution function of the transform of this convolution. So that would be the transform of the one busy period. Beta 1 of s is beta raised to the jth power. And that's going to have amazing consequences. Maybe I shouldn't say amazing. It's going to simplify things quite a bit. Okay, so let me outline why that's going to happen, how it's going to happen, and then we'll quit for today. Okay, so what I'm going to do is I'm going to write equation 863, which is a distribution function, an equation of the distribution function of the busy period. B of t equals. Now, B of t, by definition, is the probability that the busy period lasts less than t. Okay, so the busy period starts off with one customer, and there's a service time. Now, at the end of that service time, then there's a remaining busy period. And that remaining busy period is the busy period generated by the j customers who arrived during the first service time. Okay, so what I'll do is I'll take, I'll say let h of x be the service time distribution function. Call it u here. So dh of u is the probability that the first service time of the busy period lasts exactly u. Okay, now if it lasts exactly u, then there's a probability lambda u to the j over j factorial e to the minus lambda u that exactly j customers arrive during that time. If the total busy period is to last less than t, then the busy period that begins after the first service time, which is the busy period generated by those j arrivals, must last less than t minus u. And the probability of that is, let me give myself a little bit more room here. Here's the dh of u. Here is the probability that the busy period generated by those j arrivals lasts less than t minus u. And then I have to integrate that over all u from 0 to t, and I have to sum that over all j from 0 to infinity. Okay, the probability then that the busy period lasts less than t is equal to the probability that the first service time of the busy period lasts exactly u times the probability that during that first service time exactly j customers arrive times the probability that the additional remaining busy period, which is a j busy period because it's the busy period that starts with those j customers present, lasts less than t minus u, added up for all u from 0 to t and all j from 0 to infinity. Okay, so here is an equation that relates the distribution function of the one busy period to the distribution function of the j busy period and the service times. Now you do the obvious, which is you take transforms. Okay, so this is equation 864 I had already written. Okay, I erased it here. but equation 864 said that beta j of s is equal to beta of s to the j power, where beta, by definition, is the Laplace-Diels transform of b. Okay, so now comes some arithmetic, which might be difficult, but it's still only arithmetic. I'll indicate it. Most of it's left out of the book anyhow. I'll multiply by e to the minus st. Well, first I'll differentiate. Okay, so I'm going to take the differential of this, and that means I'm going to take the differential of this. I got to keep erasing this to give myself more room. Okay, here's what I had. I had b of t equals. Okay, so now I'm going to take d of that, and that means I'll take d of that. Then I'll multiply by e to the minus st, e to the minus st. Then integrate from 0 to infinity, then integrate from 0 to infinity. By definition, that thing is beta of s, the Laplace-Diels transform. Okay, so what I have to do then is I have to work with this thing right here, which looks like a mess, but it's not that bad. Because first thing you do, this is where you have to be good in calculus. So again, this can be difficult, but it's merely technical. Okay, this is advanced calculus. So now what I'm going to do is, first of all, I'm going to use the fact that everything that I can do for ordinary derivatives, I can do for differentials. So I manipulate things the same way. And you say, okay, now I've got to take the derivative of the thing in parentheses. And when I do that, I take the derivative with respect to t. That's what I'm differentiating here with respect to. And the t appears in the upper limit, but it also appears inside the integral. So that means that in order to do that, I have to use Leibniz's rule. Leibniz's rule is the rule that tells you how to differentiate an integral in the case in which the variable of differentiation appears in the limits and inside the integral. Okay, but once I do that, that's all there is. I'm always assuming, of course, that I can interchange the orders of operation of differentiation, integration, and summation. So all you do is take the differential of that, and then interchange the order of integration, and then sum everything you can. Of course, when you sum things, you see that what you're going to be summing is terms that are like Poisson terms, which means you're going to have exponentials, which means that you're going to have transforms. Because if you have an exponential and you have the distribution function, then that gives you a Laplace or a Laplace-Diels transform. Okay, so let me write down what you get. Now, if you go through all this arithmetic, what this tells you is beta of s equals. That's that beta of s. Now, just doing the arithmetic here, this is just integration and manipulation, and I'm not saying it's easy, but it's the kind of thing that you could give to a junior level analysis student. Okay, so what you get is equation 865. So you get the sum as j runs from 0 to infinity of the integral from 0 to infinity of lambda u to the j over j factorial e to the minus lambda u e to the minus su times beta sub j of s d h of u. That's equation 865, except that in the book it's called zeta instead of u. Now, also I wrote it this way. I wrote beta sub j. Now that beta sub j, of course, comes from here. That is when I apply Leibniz's rule and evaluate one of those integrals on the inside, what I'm going to find is that it's in fact the Laplace-Diels transform of b sub j. But now we replace beta of j by beta of 1 to the j power. And that means that that thing can be combined with the lambda mu to the j power and sum. And so when you do that, you're going to get an exponential. And in the exponential, there's going to be lambda, u, and beta. OK, the result of all that is given by 866. Let me write down what that is. Here's what 866, what all this reduces to. It's beta of s equals the integral from 0 to infinity of e to the minus. And in that parentheses there is s plus lambda minus lambda beta of s, all integrated with respect to the distribution function of service times. There should be a u here and a u here. OK, so after a lot of arithmetic with this, that is, I replace the beta sub j by the beta to the j power. I combine that with this, and I sum it. And when I do, I get an exponential. I combine those exponentials, and the result is this. And now you look at this and say, well, what do I have here? I have that this thing is the integral of e to the minus something times dh of u. E to the minus something u dh of u. So that is the Laplace-Dieltjes transform of h evaluated at s plus lambda minus lambda beta of s. So if we call the transform of h eta, as we have been, then that gives us this result. Beta of s is equal to eta, the transform of h, evaluated at s plus lambda minus lambda beta of s. OK, that's a very important result, and that's equation 867. Just let me say a couple of words about that, and then we're out of here. This is a very neat-looking result, and it's very strange, because what it does is it takes, starting from the original probabilistic formulation, which was an integral equation, which related the distribution functions b to themselves. What I get is this nice relationship that tells me that this transform is equal to this transform, that's the service times, and the unknown transform is itself the argument of this transform. So what I need to do is I need to invert this somehow. I need to be able to pull this beta out. Of course, if I knew what eta was, and it was a nice algebraic thing, then I could get this as a function of beta, and then I could solve algebraically for beta, and I would have beta in terms of the parameters that determine the eta. But in general, of course, I don't know what the eta is, so I can't pull this outside the function. Nevertheless, it'll turn out that, well, first of all, I can get expected values. I can get all the moments, because I can differentiate implicitly. So I'll do that next time. And the second thing is, believe it or not, that I can actually invert this and get an expression for b of t explicit. And I'll do that next time, too. All that requires the same kind of argument, that the same kind of trickiness that was used in the inversion of omega to get Benish's formula. In other words, we'll do it without doing it. We'll do it by recognizing things. OK, let's quit there for now.